Okay, so I tell you, again, I will take about 5–10 minutes of transparencies, and then I will go on the board and show you in more detail. So the general idea of TPSC is that you want to drop, I drew some diagrams, but you have to understand that they just mean, irreducible vertex, or there's some big object. They're not, they're not expansions and powers of anything. So you drop diagram, and instead you impose constraints and some rules, like conservation laws, the Pauli principle, and local moment and local density sum rule. That's what I showed you. Then what you get for free is the Merman-Wagner theorem, this Kanamori-Bruckner screening, and consistency between one and two particle quantities. So I've explained this, but I want to stress that when I wrote this expression for the self-energy, it's written in one particular channel. If you look at the more general results, this is the fully reducible vertex. So you can decompose it in the longitudinal channel, which I just did, where you have up, up, or you can decompose it in the transverse channel, where you have up, down. And in fact, there's crossing symmetry, so that the longitudinal channel is related to the transverse channel. If you want to satisfy in some approximation, but in some good approximation, it gives better high frequency behavior, this crossing symmetry, then you end up with this relation where the spin come in 3 times because there's spin 1, and the charge comes in 1 time. And the key chi-spin that enters there is what we computed at the first level of approximation using this sum rule and this ansatz. Now, what do I mean by internal accuracy check? What I mean is that I will show on the board where this comes from, but this self-energy at the second level of approximation times the Green's function that enters the insusceptibilities is exactly equal to U and up and down. So the U and up and down we get in this U spin, U charge calculation is reproduced exactly by this. But the real sum rule is that the self-energy and the Green's function are at the same level. So the Green's function here should contain this self-energy. Now, whenever TPSC is valid, these two quantities don't differ very much. They're very close to each other, and as a function of temperature or U or anything, they follow each other. But when you enter the regime where TPSC is not valid, then they start to have different temperature dependence, different U dependence, so you know you need to stop. Another one is related to the F-sum rule, which we don't use in practice, so I will not talk about it. How do we do the supraconductivity? I'm supposed to start this. So the supraconductivity you obtain by looking at how the Green's function is modified by a pairing field. And that will give you 2 components. One which is just a bubble, and the other one which has the vertex. And if you expand this, then this vertex is just including the 2 lines is related to the functional derivative of the self-energy with respect to eta. So when you do that in TPSC, what you use for sigma is the one that contains the antiferromagnetic spin fluctuation. It's sigma at the second level. So it's really like you include the exchange of spin fluctuations. But still, all the spin fluctuations are calculated with Baire propagators. So you're missing, in fact, the infinite series. You're just looking at the first term of the infinite series. So, but that's how we got this diagram. Because here, if you look at the vertex contribution, it's only 20%. So we're still in some relatively weak coupling regime and weak fluctuation regime, but it goes in the right direction. I mean, without the vertex, it would be more on this red line. So this is useful. So how do we determine TC? Well, we look at this term. So if I look at the value of this susceptibility as a function of doping at a fixed temperature, then it goes down here because of the pseudo gap. Now, if you look at this term, it represents the effect of exchange of antiferromagnetic spin fluctuations. Then it goes up because you're getting close to a filling, and eventually it goes down as well because of the pseudo gap. So our statement is that when these two lines cross is when you have TC. In other words, it's like you have 1 over 1 minus x. You expand, you get 1 plus x. So when x equals 1, it diverges. That's how we got the TC. So I would say that what are open questions. I don't know why we have not done that yet, but I guess it's just because people who were running the programs are gone. But we can calculate TC for the electron dope, some realistic calculation. Include the feedback of supraconductivity and antiferromagnetism. This is not done. Perhaps that will explain the correlation length near optimal doping. And finally, it would be nice to take the atomic limit as a starting point to generalize this approach to strong correlations. And I think that's what Olivier and Thomas are doing, is the best I have seen towards achieving this goal. Okay, so now I will go on the board. I think, do I need to place 3 or 1? Okay, 1 is the good. Okay, so I can explain the Merman-Wagner theorem very simply. So in TPSC, we do a T, N. We sum over all Q and over all frequencies. The spin susceptibility, chi spin. I will write little q here as wave vector and frequency. And that's equal to n minus 2 n up and down. So if we are near a phase transition, we know it's the zero frequency limit that is important. That's the one that is going to diverge. So we just take t. This becomes an integral d dq, forget the pi's. And if we look at just the zero frequency contribution of this, it will have an Ornstein-Zernicke form. It will be c minus 2 plus q squared, where q is measured with respect to pi. And then there are all the other finite Matsubara frequencies. But you see that clearly this is weakly dependent on temperature. In fact, it's bounded. Clearly, this can be 0 at most, or it can be the R3-Fock value. And all the finite Matsubara frequencies are not singular. So here I will write that this scales like a weakly dependent function of temperature. Now, if I'm in 2 dimensions, I get d squared q divided by q squared. So this is just a log. So I will get log of xi that will be proportional to some other function of temperature. So you get that xi is proportional to exponential of c prime of t over t. So it diverges only at the 0 temperature. In other words, if you take c minus 2 to 0, which is like infinite correlation length, this integral diverges, and it cannot because of the right-hand side. In 3 dimensions, the integral is convergent even with c2 equal c minus 1 equals 0. So you can get an EL transition. Okay, so that's enough for Merman-Wagner. Now, what about the pseudo gap? So in the same approximation, I can write for the retarded self-energy. You saw the general expression. So retarded self-energy as a function of k and omega, drop the R3-Fock piece, then I keep just the 0 Matsubara frequency contribution. So I get integral d dq. And then I have chi spin. Chi spin, we said near the phase transition, we can take as this Ornstein-Zernicke term. And then I have a Green's function, which is just 1 over omega plus I eta minus epsilon. We have to remember that we are expanding around pi, so I get near plus q plus little q. Now, suppose I'm suppose I want to know the imaginary part of the self-energy. at the Fermi wave vector and at zero frequency. In Fermi liquid theory, this is 0 at 0 temperature. Okay? Now, what will it be here? Here it will be T times integral d dq times A divided by C minus 2 plus Q squared times delta. Okay, omega is 0. If I'm at a hotspot, then this is 0 as well. So, yeah, because a hotspot, by definition, it takes me from K Fermi to K Fermi with the Q. So the only thing I'm left with is delta of V Fermi at the hotspot, dotted into Q, which I will define as a Q parallel. So the integral is easy to do. So I get T times integral d dq times d minus 1 Q perpendicular A over C minus 2 plus Q perpendicular square. And Q parallel here is just 0. And using properties of delta function, I get the V Fermi here. So you see, you recover my theorist inverse of the thermal de Broglie wavelength. So I get that sigma double prime scales like 1 over Xc thermal. And what is in the numerator? Here, let me make this dimensionless. So I just multiply by Xc squared. So this will be 1. This will be Q perpendicular Xc squared. So that's a new integration variable. So I just multiply by Xc to the d minus 1. And I multiply by Xc to the 1 minus d to undo the damage. So this is dimensionless. And the integral converges, and this is just Xc to the 3 minus d. Xc to the 3 minus d. So if I'm in 4 dimensions, this goes to 0 at 0 temperature, and that's Fermi liquid. 3 dimension is marginal, and d equals 2 is just Xc over Xc thermal. But we just saw that Xc diverges exponentially, so faster than 1 over t. So this will go to infinity as t goes to 0. So an infinite scattering rate means that the spectral weight goes to 0 at 0 frequency. And in fact, we can see this a little bit more clearly if we look at the real part of this retarded function at some k vector and some arbitrary frequency. Not so arbitrary. I will choose it such a way that omega is much larger than Vf Xc to the minus 1. Then if I do this, then this becomes T times integral d dq and 1 over Q squared plus Xc to the minus 2. And then I'm left with this. And this I just write as 1 over omega minus epsilon of k plus big Q. And little q is of order C to the minus 1 because of this that makes the integral very peaked. So if I'm in this regime where omega is much larger than Vf C to the minus 1, I can just drop the Q dependence of this. So this number, just you will see why I do this. I call this delta square minus epsilon k plus Q. So if you look now at the at the single particle spectral weight, so what is measured in RPS, so what is measured in RPS A is minus 2 sigma double prime divided by omega minus epsilon k minus the real part of the self-energy square plus sigma double prime square. So you see when you're here at 0 frequency, sigma double prime becomes infinite. And this has some some behavior, but the sigma double prime infinite makes the spectral weight go to 0. If you're far from the hotspots, then you just have this approximation. So the real part becomes, delta square over omega minus epsilon k plus bq. And if you look at where this will be maximum, is where this will vanish. And clearly, this will vanish where omega minus epsilon k times omega minus epsilon k plus big Q minus delta square is equal to 0. And you recognize the dispersion relation for an antiferromagnet. You just write a little 2x2 matrix, write the determinant, and that's what you obtain. So we know from this, all these analytic results, that the spectral weight will look something like this at K Fermi, with the 2 peaks distance given by this delta square. Okay? Questions? Okay, now I'm going to be even more sketchy than I have been here. But I hope to give you the general flavor of how things are done without entering in details of all the indices that come in this calculation. So let's look at many-body theory in general from the point of view of Schwinger. I mean, Schwinger was not very popular because he didn't have all the pictures, but you can rederive all the pictures using the Schwinger approach. And if you want to do non-perturbative things, it turns out to be much more natural. So what we do is we write a partition function as a function of some source field that we write then as a log trace e to the minus beta h minus mu n. So this is nothing surprising. This is the usual definition. But the source field we write as a time-ordered product of exponential of minus psi dagger 1 bar, some source field phi of sigma of 1 bar, 2 bar, and psi sigma of 2 bar. Okay, so what do I mean by all these symbols? Psi is creation annihilation operator, and psi 1. So the 1 means that I'm at a position R1 and imaginary time tau 1. I know that some French people use this, but this is very dangerous in France. Did you lock the door? Because I don't want any mathematician to be passing by, because then my reputation would be dead. Because in this notation, you realize that I can write delta of 1 minus 2, which means that 1 can be equal to 2. You pardon me, huh? Don't spread. It's already gone, yeah. I know people in Saclay are using it too, so that's fine. Okay. So the bar means that I'm integrating overall position or summing overall position if it's a lattice, and integrating over imaginary time. So with this approach, the Green's function, position 1 and 2, which is defined just as minus the expectation value of the time-ordered operator psi 1, psi dagger 2. So I will remove the time-ordered and just assume that all the time it's like that. And it's just equal to minus. So you have to manipulate these objects as if they were partial derivatives, okay? Delta phi 2, 1. And now the G is a function of phi also. So I can generate higher order correlation functions. Like, for example, if I want a 4-point function, I just take a derivative with respect to phi. Now, I write the equations of motion. So I will need the equations of motion. So I take d tau of psi. That will give me the commutator of h with psi. And in the end, this is just the equation of motion. So I get G0 minus 1, which is dd tau minus the kinetic energy, minus phi of sigma times G. I write in frequency, so the delta function becomes 1. And then here I get the sigma times G, like if there was matrix multiplication. But what is this sigma times G? It comes from the commutator of psi with the interaction. So it means that sigma 1 bar G of 1 bar 2 of sigma is equal to minus U psi dagger minus sigma 1, psi minus sigma 1, psi sigma 2, 1, psi dagger sigma 2. So the definition of the self-energy is this. Now, what about response functions? Because we want to compute the spin and charge susceptibility. So we got rid of all these 3 points, and the other ones will not take much more time, about the same time as I just used. So what about response functions? So response functions are, I just start from G minus 1 is equal to 1. Okay, this is the definition of G minus 1. Now I said I want to generate 4-point functions, so I just need to take functional derivatives of G with respect to phi. Right? That was my whole argument for using this source field approach. So let's drop the spin indices for now. So if I apply this operator on this, I get 0 on the right-hand side. So this means that I have this equals minus G times delta G minus 1 delta phi. And, or if you want, delta G delta phi, this 4-point function, is just equal to minus G. Okay, G minus 1 we have here. Because this can be written like this. G minus 1 is G0 minus 1 minus phi minus sigma. Okay, I just multiply by G minus 1 on both sides, and that's what I get. So if you take this functional derivative with respect to phi, you see that you get GG, you get delta phi with respect to delta phi, which will give you a bunch of delta functions that will determine the indices that go there. And then you have plus G delta sigma delta phi times G, where this is like matrix multiplication. But now the sigma depends on, instead of using phi as a variable, you can do some Legendre transform and use G as a variable. So then I use the chain rule, and it has this structure. So this looks like a susceptibility is equal to this bubble times the susceptibility again. Then I have 2 Green's function, and this is the so-called irreducible interaction. And you have to work out the spin indices. You take the symmetric and anti-symmetric part. It's a little bit of a mess, but in the end what you get is that U spin is delta sigma up, delta G down, minus delta sigma up, delta G up, and U charge is just the same thing but with a plus sign, up, delta G down, plus delta sigma up, delta G up. And basically, that's many-body theory. That's what you need to do to solve the many-body problem. But this is all exact up to now, so there's not very useful in some sense, because it's still quite complicated. So how do we get the TPSC? So the ansatz is the following. So I'm getting to this point here at the ansatz. So the point is very simple. It is just that the ansatz is that if the point 2 here is away from 1, then we can just use R3 But if 2 is at 1, then we get and down and up. So and down and up is very important. So it serves as an initial condition for this factorization. In other words, it's a little bit like Onsager theory for non-equilibrium system. You get the static part correctly, and then you let evolve. Or in the case of the electron gas, it's in the theory of Singui is very similar. And Vignali and somebody else came up with this ansatz. It was not derived this way, I think, but they arrived at that. Or another way to think of it is like Onsager reaction field. But so what we, so if we do this factorization, you see that what we have is that sigma of 1 bar times G, and let me put the spin index, 1 bar 2 is equal to, okay, I factorize a la R3 which means that I have a G of minus sigma of 1 plus. So the plus here just means this time order. And I have a G a sigma of 1, 2. But what I want is that when 2 is equal to 1 plus, I want to get the exact result. I don't want to make an approximation. So what we will do is put some prefactor here. That's a functional of phi also. But that will be determined in such a way that when 2 is equal to 1 plus, then this sum rule is satisfied. So sigma of 1 bar, G sigma of 1 bar, 1 plus is equal to U and up and down. And that's the consistency relation I explained at the beginning. Internal consistency check was this. So how can I get this? Well, I just have to choose A of phi to be equal to U times n up and down divided by n up times n down. Why? Because when 2 is equal to 1 plus, this is n down, this is n up. So I simplify this, and I'm left with U and up and down. Now, why is this equal to U spin? Okay, because if I take this expression here, when I differentiate sigma up, okay, here I forget one thing here, which is that I want to write sigma itself. So sigma itself, I just need to multiply by G minus 1 on both sides. And this means that sigma 1, 2 is equal to U and up and down divided by n up and down times G minus sigma of 1 plus times delta of 1 minus 2. Okay, I just multiplied by this expression by G minus 1. Now, when I take, and this is for spin sigma. So if I take a derivative with respect to the Green's function for the opposite spin here, then I get a contribution from this. So this will disappear, and I'm left just with U and up and down. So I have a first term that is U spin equals U and up and down divided by n up times n down. Now, the functional derivative acts on this object also, because that's still a functional of phi. But you see that this is a spin singlet. Whether I differentiate with respect to up or down, when I put phi equal to 0, it has to be the same answer. So in doing this subtraction, this object disappears. So in this approximation, this is really U spin. But if I look at U charge, then the functional derivative I just mentioned does not vanish. It adds up. So all it tells us is that U spin is different from U charge. And also, although U spin, we didn't follow all the delta functions, but U spin remains a local object. So independent, I mean, non-zero only when all the four indices are equal. For charge, it's not true anymore. But what we do for charge is we say, okay, we still take this local approximation and we fix it with the Pauli principle. So that's what we did. Now the last...
So, just a couple of questions. So in principle, on the exact equations written there, U spin and U charge are functions of at least two frequencies, right?
Oh, there are three frequencies.
Three frequencies, so they are vertex.
But if once you write it this way, you see if it's like RPA. So if there was not for this factor, you would get the bare U. Okay? Because when you take the functional derivative here, that would give you U and 0. And here you would get 0 and U. So this is how you get RPA. But here with this correction factor that imposes the consistency between this one and two particle quantity, then these two things become different.
So at dominant order, it's U, as you said. And the next order, is there any case?
If I think that we checked that you recover second order perturbation theory.
Exactly.
I think that's what I remember. I'm not sure, but the
self-energy cannot be a number times G, so that's why.
Oh no, second order perturbation theory for the spin susceptibility. So, but in the end, as I said earlier, the idea is that the spin and charge fluctuations are mainly determined by conservation laws, and they don't depend on so much on details of whether I have a peak or not in the self-energy. On the other hand, the self-energy couples to the collective modes that go all the way to omega equals 0. So now I sort of improve the self-energy. And if you open my hand and look at how the electron gas is done, that's precisely the way it's done, right? You compute the plasmon with the bare Green's functions, and then you compute, and then you get an infinite mass for the self-energy in its Hartree-Fock approximation. So you say, oh, panic, panic. And now you improve the self-energy and by putting the screening and retardation, and then you get a sensible result. So here it's the same idea. We want to improve the self-energy. So at the second level of approximation, how do we do this?
So just to make sure I understand, so this will not be your final answer for the self-energy, because this is just...
No, this is the self-energy that entered everything for the response functions.
That's what you call sigma 1?
That's what we call sigma 1 in the...
You had sigma 1, and G1, and G2, and sigma 2.
Yeah. So everything 1 was this level. Now I'm starting with 2. So sigma 1 bar times G of 1 bar 2 of sigma is equal. So we have the exact expression there, right there. It's this 4-point function. Fortunately, I just erased an equation I need, but so this will be minus U times delta G sigma, or you can write 1, 2 if you want here, times delta phi minus sigma 1, 1 plus. And then this generates not only this 4-point function, but also a disconnected piece that you need to subtract out. So you have minus G sigma of 1, 1 plus, minus sigma G of sigma 1, 2. So this is without approximation. This is exact. Now you multiply by G minus 1 on either side to get the to get the self. So sigma of 1, 2 will be, okay, this, when I multiply by G minus 1, this is just the Hartree Fock piece. So this is U n minus sigma. And then I have a piece that is minus U times delta G sigma delta phi minus sigma times G minus 1, because I multiply by G minus 1 of sigma. And if you remember how I did the response functions, so the response functions were obtained like this. Delta G, delta phi, G minus 1 was minus G minus 1, delta G minus 1, delta phi. So if I just use this identity, I get U n minus sigma minus plus now U times G of sigma delta G minus 1 sigma delta phi of minus sigma. So this is just this equation. And now I have the equation for G minus 1. Again, it's over there. It's this expression. And now, but G sigma depends only on phi sigma, so I get no contribution from phi. The only contribution I get is delta sigma delta phi of minus sigma. And again, I use the chain rule. So this is delta G sigma prime, delta G sigma prime, delta phi minus sigma. And this is, you recognize now this, right? So this is related to these spin fluctuations. And this is the irreducible vertex. So you saw that we had U spin and U charge in the expression. And this is the Green's function. So you need to work out this, and you find this U spin and U charge. Now, you could do exactly the same thing in the transverse spin fluctuation channel. And you get a different expression for sigma. But by requiring that, that there's this crossing symmetry and that this sum rule must be satisfied, then you get the expression I wrote down with the 3 and the 1. Okay, so are there any questions on this? I assume there are many questions, but in fact, there is a review that I wrote a couple of years ago, which is there, and it's in the book, but it's on the archive, so you can find all the details with the 1s and the 2s and the bars and everything. But you see that, I mean, I was able to do it in about 20 minutes. So if you work out all the 1 bars and 2 1, it may take you 1 or 2 hours, but it's not the end of the world. Do you have any question? So if not, next time I will go back to talking about DCA and see the MFT and all that. So I will try, actually, I don't know how much I will succeed, but I will try to, at the beginning, in the first half, to give you an idea of which method is better. Because in DCA, there are certain quantities that we know are more accurate. In CDMFT, other quantities. So I will try to give you a feeling for this. And then I will show you algorithmic improvements that have been done in the last few years. At least give you an idea of what these algorithmic improvements are. And then perhaps I'll go on the board again for some details, but I'll try to make the first half sort of quite generally accessible.
More questions? Perhaps I have one question. So can you comment really this
yeah, I know that the momentum dependence is clearly important, right? Because it's this. And the frequency dependence, certainly on the scale of this antiferromagnetic gap, is important as well, because at least when the antiferromagnetic correlation length is large, I showed that sigma prime is, the real part is delta square over omega minus epsilon k plus q. So in fact, it diverges at epsilon k plus q. So when the antiferromagnetic correlation length becomes important, both the momentum and the frequency dependence are very important.
And perhaps another question is, if I go back to your formula for sigma double prime in terms of the thermal and antiferromagnetic correlation, so this is a very drastic violation of thermal equilibrium.
Yep. Okay. The most drastic you can imagine, perhaps. Okay, yeah, I think, qualitatively, I'm pretty sure it has to be valid because of what I showed you, that you're going to a ground state that is gapped, and it's just a way to do it in the presence of thermal fluctuation. So I think this is okay. If you ask whether TPSC is correct or not, well, I showed you that with DCA, you know, we get this agreement with double occupancy, and we check things of that sort. And what we know is that TPSC is good if when we enter this renormalized classical regime. But if you go too deep, it definitely fails. I mean, these consistency checks don't work, and you can also guess why it fails. It's because it all starts from quasi-particles. All the collective modes are calculated with quasi-particles. As long as when you start to build the antiferromagnetic correlation length, then your starting point should have two peaks in some ways. So that is some generalizations that we have. I mean, it would be nice to start from an ordered state. I guess Nicolas had done some work within more Hubbard-Stratonovich type picture, where you start from something that is that has the antiferromagnetism, and then you start to include the fluctuations. But we've never done it in TPSC. That's been in the plans for a long time, but because of you, I'm sort of doing a DMFT and CDMFT and never get back to never get back to this.
Last question, perhaps, if I'm close to quantum critical antiferromagnetic quantum critical point, right? And I take these formulas from TPSC. So how does that compare to the normalization group treatment? I mean, does this give the right exponents above dimension 4 because these two in that
Okay, yeah, the universality class of this is n equals infinity. Is n equals infinity. So when I showed, so the critical exponents are
like a spherical model.
It's a spherical model, yeah. So in fact, when I compared with the Monte Carlo calculations here, you see that the critical behavior is going to be wrong, right? It starts to deviate from the real thing. So, yeah, so in this paper we showed okay, so thank you very much for your patience.